We've been covering a lot lately, so maybe it's time to take a break and go for a walk. By the end of this session, we'll be able to trace traffic flows through an SDA fabric. We are talking about a packet walk. Up until now, we've been looking at all of the pieces and components of how a fabric forwards traffic. Well, now it's time to take all those pieces and bring them together and see the complete solution. Let's start at the beginning. Let's say host A is connecting to the network and it sends some initial traffic. Switch 1 is going to detect that traffic as a new entry, a new host that's attached, so it's going to create a local cache entry so it knows where it is. Then it's going to send a map register message to the control plane node. And the control plane node is going to create that endpoint identifier to routing locator mapping, or EID to RLOC. Now remember that RLOCs are essentially loopback addresses on the fabric edge nodes. And so, for example, let's say switch 1 here has an IP address of, 1.1.1.1.1. Well, now we know that endpoint A is attached to 1.1.1.1. Well, let's say host B does the same thing. It attaches to switch 2, it sends some initial traffic, switch 2 adds it to its local cache, and then it sends a map register. So now we know that B is attached to, let's just call this one 2.2.2.2. So now host A wants to send traffic to host B. And so it's going to send that traffic upstream to switch 1. Well, switch 1 is going to get that traffic and realize, hey, I don't know where B lives. And so it's going to send a different type of message called a map request. And the map request essentially boils down to, where is B? And keep in mind that we'd maybe expect the control plane node to respond directly, but we recall that by default in an SDA fabric, the control plane node will actually message switch 2, in this case, the ETR that advertised host B, and it will send what we call the map reply in order for switch 1 to know where B is. And as such, switch 1 is going to get rid of that question mark and say, okay, well now I know where B is. B is attached to 2.2.2.2. And so I will add that to my local cache so I don't have to check in with the control plane node next time I'm sending traffic to 2.2.2.2. So let's go and clean up our drawing here and remember that switch 1 has a tunnel connection to switch 2. And so it knows that it needs to send the traffic from host A out that tunnel interface. But let's get down to real bits and bytes here. I mean, there is physical equipment inside this fabric. For example, we might have a core switch that is directly attached to these two switches. And within this fabric, we're running an IGP, an Interior Gateway Protocol. Now we recall that Cisco recommends ISIS as the routing protocol, and if indeed we use DNA Center to set up this fabric underlay, then ISIS would be in place. However, we could use a different routing protocol if we so desire. Either way, switch 1 has a routing table that tells it where switch 2 is. So for example, I know where 2.2.2.2 lives, and so I'm going to follow my routing table and send it up to the underlay network. However, first we need to encapsulate this packet. This packet has a source address of A and a destination IP address of B. However, that doesn't do us any good in the underlay. We remember that the underlay doesn't have a clue where A lives. It doesn't have a clue where B lives. And so we're going to encapsulate this traffic. We're going to throw a new source on here. We're going to say the source is me, 1.1.1.1 in this case for switch 1. And the new destination, that's switch 2. That's my RLOC destination, in this case 2.2.2.2. And so when this packet arrives on the switch, this switch sees a destination of 2.2.2.2, which is part of the underlay. It's part of the ISIS domain in this case. And because it has a routing table and it knows where 2.2.2.2 lives, it's going to forward that traffic out the appropriate interface. Now keep in mind that as part of this encapsulation process, we added two tags. We added the scalable group tag and the virtual network identifier, or VNID. These two tags are part of the VXLAN header, so when we say that we've encapsulated this here with the new source and destination address, we've also included these tags in the encapsulation. So now switch 2 is going to bring this traffic in, and it's going to check those tags. It's going to check the scalable group tag, it's going to check the virtual network identifier, and it's going to find out what the actual destination address is, in this case, host B. Well, now we know where this traffic is trying to go, and we have the appropriate tags in order to figure out whether or not we're going to allow this traffic. If we want to drop the traffic at this point, we would simply drop it. However, if we determine that this traffic is allowed, we will send the de-encapsulated packet to host B. And at this point, the packet is originally what A sent. Not only is the source address A and the destination address is B, but if this is within the same layer 2 subnet, we're going to see the MAC address. So the layer 2 source will be A, and the layer 2 destination will be B's MAC address. Keep in mind this wouldn't be true if A and B are on separate subnets. However, again, VXLAN was chosen for its layer 2 compatibility. And so if A and B are on the same subnet, then we would see the same layer 2 header, that original layer 2 header that A had constructed. Okay, now let's take a different example. Let's say A wants to go out to the internet. It's some unknown IP address. We've done our DNS resolution. Whatever website I'm going to, I have an IP address now. Well, switch 1 is going to look at that IP address and say, oh, I don't have that IP address. Maybe it's inside my network. Maybe it's not. Switch 1 doesn't know. What switch 1 is going to do is send that map request to the control plane node and receive a reply back. However, in the case where an IP address isn't part of our fabric, the control plane node will respond with the RLOC of the appropriate border node. Now, because this destination is on the internet, it's unknown. We do not know where this IP address lives, and so the control plane node is going to send back the external border node's RLOC. That means that switch 1 is going to go through the exact same process, again, tagging in the SGT, tagging in that VNID, except this time it's going to send it via the tunnel to switch 3, our external border node. Everything we just described is going to be the same, where we have that switch in the middle, and the source address will be me, 1.1.1.1, except my destination now, instead of going to switch 2, we're going to switch 3. So let's just say that's 3.3.3.3. And because this is all part of the IGP domain, our underlay is going to know where 3.3.3.3 is. As such, it's going to forward it out the appropriate interface, and it will land on switch 3. Switch 3 will do the de-encapsulation. We're going to run the security group tag and the VNID checks to make sure that this traffic is allowed to go to the destination, even though it's unknown. And then, if it's allowed, we will send that traffic on accordingly. So the key takeaway here is this conversation around the underlay and the overlay communications. As traffic gets put into the fabric, we are going to encapsulate that traffic and use different source and destination IP addresses. We are now part of the underlay at that point, and the underlay will get us to the final destination. But remember, the underlay doesn't know where host A is. It doesn't know where host B is. It doesn't know where any of the addresses are that are outside of the fabric. It only knows the IP addresses that are in the underlay, and then also the RLOCs, because the RLOCs are how we get from one switch to another. So once we understand the encapsulation process as well as the enforcement process using those tags, then we have a very clear picture of how an SDA fabric operates. And with that, you are now able to trace traffic flows through an SDA fabric. I hope this has been informative for you, and I'd like to thank you for viewing.